Okay, this video is going to finally delve into the pH scale. So there have been several videos in the playlist that have led up to this. The definition of acids, the definition of bases, the definition of pH, and then we've practiced some calculations. Now what we need to do is put all that together in order to wrap our minds around the pH scale. Now, I would highly suggest that you have out a calculator and be prepared to work through these various calculations as I take you through how the scale works and where it comes from. To make life easier, what I'm going to do right now is go ahead and establish the relationships that we've learned in previous videos. So remember that pH is equal to minus the log concentration of H3O plus. Remember that POH is equal to minus the log concentration of OH minus. These two concepts are linked by the equation that says 14 is equal to the pH plus POH. And I'm going to address again why this relationship is true in a few minutes. All right, let's see. And then the last one is, and basically this is where the top equation comes from. We have the ionization constant for water, which is equal to 1 times 10 to the minus 14th. And this is at 25 degrees centigrade, so it's at fixed temperature, and what it says is that the concentration of H plus, excuse me, I want to stay consistent here, the concentration of H3O plus times the concentration of OH minus is equal to 1 times 10 to the minus 14th. And then coming back to the left side of the screen, I think it's important for you to know how to go back and forth from pH to H3O plus or back and forth from POH to OH minus. So concentration of H3O plus is equal to 10 raised to the minus pH, and concentration of OH minus is equal to 10 raised to the minus POH. So these are all the relationships that we're going to use in order to describe what the pH scale means and how to use it. And I think before we get started into this, I want to move the scale. I'm going to move the scale down so we have more room to mess with this. All right, now here's the thing about the pH scale that you need to understand. The vast majority of experiments and manipulations that happen in a laboratory setting happen between 0 and 14 on the pH scale. Most everything that happens in the biological world, that happens even in your swimming pool, for example, or in your hot tub, is going to be centered on this scale around pH 7. So going into this, the main motivation to create this scale was to have a way of being able to relate the concentration of H3O plus and the concentration of OH minus in a situation where we could compare essentially whole numbers or decimal numbers that are at least convenient to deal with. And what I mean by that is that if you're sitting around the lab and you've got an experiment and you're talking in terms of concentrations of H plus that are around 1 times 10 to the minus 9th, it's easier to have a conversation about that if you can just say that we're dealing with a solution that's pH 9. So this was the reason for the development of the pH scale, to have a way of dealing with everyday manipulations in a context that's easier than dealing with concentrations that have a lot of zeros after a decimal point. Think about the pool guy that comes to clean the pool and then make sure that the chemical conditions of that pool are safe for you to dive in or swim in or whatever the case is. So the pool guy is going to maintain a pH that's going to be centered around 7. You're not going to find somebody that wants to try and figure out, okay, is the pool close to 1 times 10 to the minus 7th molar in concentration of H3O plus. They're not even going to know what you're talking about. They want to be able to hold up that little test strip or test container they've got and compare a color to a color scale and be able to say, yeah, okay, it's pH 7, and be able to go from there. All right, so let's start to talk about the scale. So in the middle of the scale, we have a situation that we call neutral pH. All right, I'm going to write that up here. And when we talk about neutral pH, what we mean is that we're in a situation where the H3O plus concentration molarity is equal to the OH minus. All right, so that's what establishes the middle of the pH scale. And where the concentrations are equal, what you need to remember is this is where we've got the hydronium or the H3O plus concentration being dictated to us by this equilibrium or this auto-ionization of water, where the water can exchange a proton with itself, producing OH minus and H3O plus. And you can see the crucial thing here being that it's being produced in a 1-to-1 molar ratio. And so for the situation with pure water, all right, the situation with pure water is that you've got equal concentrations of both the H3O plus and the OH minus. Now, when we swing to either side of pure water is where we start to get differences in the relative amounts of these two molecules. So let's talk about the two ends of the pH scale. Firstly, I want to deal with the end that is 0, and it's important for the viewer to realize that this end of my scale is determined by a 1 molar and what we call standard solution of a strong acid. And for my example, I'm going to call it hydrochloric acid. Now, I want to dispense with the jargon. Let's just forget about the idea of standard for a minute. You just need to realize that this end of the scale is going to be determined by a 1 molar solution of a strong acid. And from the previous playlist, just run the calculation really quick and you'll see what I'm talking about. It's going to be pH is equal to minus the log, all right, and then it's going to be concentration of 1 molar for the strong acid because of the 100% ionization, and that equals 0. Now, what's a little bit trickier is seeing how this end works down here where pH is 14, because this is determined by a 1 molar solution of NaOH or KOH. All right, remember this is a strong base, and if we take the POH of that, because it's POH when we're dealing with hydroxide, it's going to be POH is equal to minus the log. All right, and again it's going to be concentration 1 molar, and yeah, this is going to give us a 0, but it's POH. So how do we get to the pH? Well, remember that 14 is equal to pH plus POH, which in this case is 0. So solving then, the pH at this end of the scale is equal to 14, and that's where this value comes from. All right, so it's important for you to realize that the pH is 14 here, the POH is 0. So the POH at this end of my scale is 0. The pH at this end of the scale is 0. So pH at this end is 14. I'm going to make sure I said that right. and the pH at this end is 0. Now, let's deal with, remember that going back into previous playlists, that when we talk about pH here, we're talking about essentially acidity versus basicity. So as we go from 7 towards 0, acidity is increasing. All right. So I'm going to put it over here. So acidity is increasing going in this direction, and the basicity is increasing going in this direction along the scale. Now, here's what I mean by that. So in this zone in here, H3O plus is greater than OH minus, and it's increasing going from right to left towards 0, from 7 towards 0. And on the other side of 7, the OH minus is greater than the H3O plus, increasing in this direction. All right. So H3O plus is decreasing as we go from 7 towards 14, and H3O plus is increasing as we go from 7 towards 0. Now, let's talk about the scale. The scale is logarithmic, and what that means is that, for example, as we go from 0 to 1, there is what we say a tenfold difference in the concentration of H3O plus. So at 0, all right, we've got 1 molar H3O plus. pH 1, and here's where you may want to use your calculator. At pH 1, the concentration of H3O plus is 0.1 molar. And you can see that the difference between these two numbers is a factor of 10. We've taken 1 and we've divided by 10. So that means the difference in H3O plus between 0 and 1 is different by a factor of 10. What that means is that at this point right here, there's 10 times less H3O plus than at pH equal to 0. 10 times less. And at pH 2, the concentration of H3O plus is going to be 0.01 molar. 0.01 molar. So at this point, literally, there is 100 times less H3O plus than at pH 0, than at pH equal to 0. All right, now, if we come all the way down to this end of the scale, and remember where we're at with this deal, is that as we move from 7 towards 14, the concentration of OH minus is increasing, the concentration of H3O plus is going down. So pH 13, what it means is that the concentration of H3O plus is 1 times 10 to the minus 13th molar H3O plus. That's what it means. And by the same token, the concentration of OH minus at this point is equal to 0.1 molar OH minus. All right, I know I was a little redundant there, but I want to really emphasize this fact. So at pH 13, we've got 1 times 10 to the minus 13 molar H3O plus, but the other side of that coin is the OH minus is 0.1 molar. All right, so you can see that the take-home message here in finishing up phase 1 of this is that nowhere on this scale ever do you have a situation where there is only H3O plus and no OH minus. There is always a ratio. There is always a ratio of the two molecules everywhere. The difference is that you can have more of one and less of the other depending on where you are as we move from 0 to 14. All right. Then the other thing I want to mention here before I finish is that I'm often asked, is it possible to have a negative pH? And now the student can answer that themselves, because look, this end of my scale is determined by a 1 molar concentration of a strong acid. So what happens if we have, let's say, a 5 molar solution of HCl or HNO3 or one of the strong acids, all right? And I'll leave that to the student to calculate for yourself. But when you do, what you're going to see is that it indeed is going to give you a negative number. And similarly, up here at this end, the only thing that you've got to do to have a pH greater than 14 is to have a solution that's going to be greater than 1 molar NaOH or KOH, and that's not that hard to do. You know, go ahead and make a solution in the lab that's 2 molar NaOH, and then again, you know, I'm going to leave it to you to go ahead and do the calculation, and when you do, you're going to find out you can have a pH that's going to be greater than 14. All right, and with that, I'm going to go ahead and close.